George Percivall is Chief Technology Officer of the Open Geospatial Consortium, a group that's been around for a good 22 years. And you know, the function, at least from my perspective, is one of the greatest strengths of GIS, maybe the preeminent strength of it, is the ability to integrate data from multiple platforms. And what OGC does is develop the standards that, among other things, enables that disparate data to come together by making sure that it's formatted in a common way that enables integration and then analysis and all the good things that come when you bring data together. So they've been a critical organization, and most recently, the Fund for the City of New York and my particular function there and OGC have gotten together with the Ordnance Survey of Great Britain and with the Singapore Land Authority to start working on an underground infrastructure data, interoperability platform. And that's coming along. George will talk about that, but there's just no question that OGC is central to the health and growth of GIS, both from the past and into the future. So George, it's a pleasure to have you. Thanks for coming, and the floor is yours. After we introduce yourself.
Joachim Altenstein, Professor for Computational and Theoretical Geography at Hunter College, University of New York.
Thanks, Alan. Alan didn't mention we first met when he approached who's now the president and CEO of OGC, Mark Reichert, about we had some issues of sharing data in response to 9/11. And is there something that you could do to help us, with respect to that? And our first OGC testbed, web services testbed, took that scenario and developed standards around that, and that was about the time the first set of web map service, web feature service, web coverage service was developed, kind of coming out of that testbed and other activities and the like. So it's been a good, and we have now the underground project. I'm going to focus on urban modeling using OGC standards, a variety of topics and the like. In particular, let's see if I can do this a little bit more. So I'll give a little bit of overview of what OGC is and what the recent standards are that we've been working on. Not all urban, but just kind of give you a feel for, this is the breadth of what OGC does. If there's any way close those blinds, because all I see is glare.
Oh, really?
In that office.
I don't think so.
Is there anything?
What if you stand on the other side?
Oh, what if I stand on the other side? I can do that, Alan. That'll work. Let's see my agenda. So, okay, what is OGC? 3D data integration. So a lot of discussion about 3D in terms of visualization. Visualizations are wonderful, but as you know, GIS is much more than visualization. It's about the attributes that go with that. How do we address that in 3D, and especially in urban environments? Then talk about two projects, one that's complete and one that is just now starting. And the one that's complete is a future city pilot. And I felt more comfortable there, so I'll go back over here. Sorry about that. Should have tried that out in advance. Thanks. So future city pilot is complete, and there's a variety of scenarios about urban planning and inundation flooding and dynamic data and urban environment, that kind of stuff that I'll show you. And then what Alan mentioned, the underground infrastructure study. It's about mapping and modeling of data underground and looking at things like excavations and how to make those less air prone, how to worry about composite or cascading effects between different utility systems and underground activities. And then some other topics as well. So, and this is a study, very early. We had a workshop here about 2 months ago, and we're writing up the report. We want to move towards a pilot activity, actually testing and demonstrating and running code kind of things in a pilot scenario. So that's the agenda. I think about an hour. Is that less, more?
I'd say less and leave time for discussion.
That sounds good. All right. So what is OGC? Founded in '94, 525 member organizations. You can see the statistics. the key thing that doesn't jump out on this is about a third of our organizations are governments at all levels, federal, state, local. A third of our members are commercial organizations, and a third are universities. And what I have seen is that's one of our strengths about development and innovation of technology. So you've got requirements coming from governments, you've got innovative ideas coming out of both research and universities and long-term research, and then you've got industry delivering that into operable code, interoperable code based upon open standards. It's a very rich innovation environment that we run for geospatial. We do create standards, but a lot of what we do is about making that technology infrastructure, the capability of the community to work together is really our biggest strength. Some members that are, you're probably familiar with a lot of those folks. Some here in the room, thank you for showing. So what is a standard? It's the easy thing to say, it's an agreed way of doing something. That's the tip of the iceberg. It really is the work of a whole lot of people to say, this is what we understand to be best practices. This is what works. This is what's been implemented. And this is something, if you want to, work in this community, this is a good way to plug in. There's always innovation in addition to those standards, with those standards and the like, but it's really about the distilled wisdom and the knowledge of the community. Let me give you a sense of how standards get developed and put in place and the innovation and the like. You might start out in a state in which you have no standard, and a good company comes along, develops a really cool product, a platform, whatever, develops what you might call a de facto standard. It's in the marketplace. The intellectual property is owned by the organization that developed that. They control that and the like. It may be public, but it's not open. Public meaning that you can see the spec, you can read the spec, you can use the spec, you can write to the spec, but if there's something wrong with it, you got to go back to the people that hold that control, and that's that commercial proprietary public standard. What we've seen on occasion at times is that an organization will say, we want to now move that de facto proprietary standard into an open environment, and they will contribute that to OGC or another standards body. This is how KML came about. Google invented it, made it really famous based on Google Earth. They turned it over to the OGC for management. They are the chairman of the standards working group for KML and OGC. No, don't get anything wrong, they still want to control it, but it's an open spec in the sense of there is an open process by which you can say, please change this, and you can get that vetted in an open fashion. So that's the difference between being a proprietary spec and an open standard. The other path to that open consensus standard is anticipatory standards. We develop things based upon requirements coming, say, from governments or other activities that can kind of see where the technology is going, anticipate the need for an agreement, a standard, a best practice to enable the marketplace. And so a lot of these also get developed in OGC through our interoperability program, for example. The Web Map service is a good example of that. Several of those. So that gives you a sense of standards and how things get innovated. We develop those, consistent with that approach. We have 4 different programs within OGC. The innovation program, which is the running code part. It's looking at pilots and test beds and implementations, and the results of that go into the standards program. That's the consensus voting activity. So the running code wins here and consensus wins here. Compliance program allows organizations who build software to certify that their software is compliant to the OGC standards. We also have a communication and outreach program. So let me give you a sense of what standards kind of exist. This is the first half of 2017. An abstract spec, 11 standards, a community standard. Just give you a sense of the variety and the diversity of the kinds of activities that are going on within the standards program. The real prime deliverable is the standards, but we also have best practices and engineering reports, white papers, working groups, that kind of thing. So these are some particular standards that have been approved in the past 6 months. There's a really interesting one called Discrete Global Grid Systems Core Standards. So grids, very key aspect with respect to geospatial. and how do you establish what the grid cell is, how those grids tessellate the surface, in particular of a globe, how you do resolution pyramids on top of that and the like. There's a lot of theory, a lot of science that goes along with this, a lot of implementation. This is now the culmination of that research and implementation to say, here's what is a way to talk about discrete global grids, so you can build software that is interoperable around discrete global grids. So very, this is one of my favorite things that has happened in the past year. And right now, the effort will be to define a bunch of different grids that meet this systems. This is how you describe discrete global grids. Now we want to get some specific grids standardized. Infrastructure GML, we'll talk a little bit about that, coverage, and then we're really going to talk too much about these. To give you a sense, if they're interesting to you, approach me afterwards. What I really want to talk about is 3D data integration, in particular for urban environments, because I think that's, first off, very relevant to a highly urban location like New York City. It's also been some very advanced work that has been done by the members of OGC. The trend generally here is the merging of these spatial domains, maps and geospatial and GIS at one scale. You got the AEC, CAD kind of community at another scale, civil and infrastructure engineering at another scale. And what we're working towards is seamless translation between the data sets at each of those levels. They'll still maintain their own standards because the use cases are different, the attributes are different. You're doing civil engineering, you need to describe something differently than doing, a land cover map. But to be able to transition some of this data seamlessly and have translators that deal with that, this is the objective, is to really treat that as scale-independent kind of thing. So that's cool. There are some challenges. 3D data integration may be the biggest challenge in the 3D domain. So this whole deal about, as Alan said, bringing together data is kind of one of the main themes of GIS. You can organize everything by location essentially, and so how do you do that in 3D? There are different semantics, there's above and below the surface, we'll see that a lot. We'll see a discussion of vector and voxel as it's referred to, discrete geometries versus voxels that are the full space. Variety of different types of data, sensor data, dynamic data, and simulation software. Like very interesting paper written by Sissy and crew out of TU Delft. That's really good stuff. If you're interested in an overview of this topic, that's a good paper to look at. So, what do we mean by kind of 3D urban city modeling and the like? We certainly mean visualization. Everybody likes to see a great visualization of your city. You want to see the pictures. You want to be able to fly through it. You want to see your buildings at high resolution. That's really cool. That's not enough to really be GIS. We need the semantics associated with that. So when you fly to a building, you can touch the building and say, what is the use of this building? What does the government know about this building in terms of its purposes, its tax base, its occupancy, its demographics? All those things fall into the semantic category. And how do we integrate semantics with 3D visualization and the like? So as it turns out, there was a city that kind of was at the front of this back in the 90s. So you remember the reunification of Berlin occurred in about the 90s or so. And they not only saw that they needed to rebuild the city, but at the same time they saw the opportunity to create a virtual model of the city while they were rebuilding Berlin. And so to go along with that, they built up the infrastructure, the 3D semantic modeling infrastructure, to go along with that rebuilding of the city. And one of the outputs of that was a standard called City GML, and they used that to model this version of Berlin that they now use for all kinds of purposes. If you want to look towards buying real estate in Berlin, you fly through Berlin, and it gives you a great story about the real estate in Berlin. It's used and actually comes out of the business development office, is who holds the model and the like. So it's really, that's where it started in Germany, but it's really used globally now. Europe actually has it as a European-wide requirement for all cities to be modeled in city GML. And so other cities in particular, we'll see Singapore pop up here as a real leader in this urban modeling based on open standard city GML as well. We have some good effort in New York City. So this is a model that was put together now maybe 2 or 3 years ago. The lead editor of the city GML model, the guy from TU Munich, Dr. Thomas Kolb, Professor Thomas Kolb, gathered 8 or 10 layers out of the open data portal of New York City and integrated those together and created a single 3D city GML model and hosted that back as open data and the like. So the buildings aren't too pretty. They are, footprints extruded to the elevation or the altitude, whatever, the height attribute. So they're just extrusions in this version. But all of the terrain, it starts out with a digital terrain model. It adds the roads, the streets, the parks, a variety of other things. It brings in all the semantic data from the city about the buildings, the demographics and the like. So it's a rich semantic model at a level of detail 1, essentially, of the buildings. There were some real challenges of doing that. So going from 2 and 2.5D to 3D, more work to be done there. Data heterogeneity, so not only coordinate systems, exchange formats, semantic models and the like had to be merged. And huge data volumes here is what we're talking about. Now there's about 1 million buildings, a total of 4 million objects. So that's one model that's available in New York City and City GML. And this is the summary of that model here on this side. This is the model that's hosted by DoIT. And you said this is 2014 LiDAR scan data?
Right, I believe so.
Okay.
So I know they're collecting a lot of LiDAR data. We've just finished collecting a whole bunch
Another set.
more.
Yeah. Did finish that.
Bathymetric and stuff. So,
Okay.
I know some of it was a little late capture, and we were trying to still figure out if the quality was going to be good enough or if things had leaked out too much already. But
Okay.
more soon.
This one's been up for 6 months or so, and it has several different data formats that it's available in. I know this is the one that the University of New York used with, there's a shadow model that was in the New York Times. You've probably seen that as well. That's the one that was used for that. And if you zoom in, the buildings are in great level of detail 3 or so, certainly 2, level of detail 2. And so you've got a very rich visual model on the left, and you've got a very rich semantic model on the right. Gosh, what would it be nice to do? Yes, sir.
I'm a little confused.
Okay.
9,500 water bodies. What are those? I can't.
Good question. It's a data set that came from the Open Data Portal in New York City.
That's probably because the planimetric data has many of the water bodies segmented, so like the river will be a bunch of polygons running up.
So
that is not
we're
right.
talking about. We're talking about the rivers as well as inland water bodies.
I would
I
imagine.
guess, and the
I'm
rivers-
guessing.
And the rivers are segmented into little pieces.
Right, into polygons.
That's a big number.
Yeah.
If you see
That would be my guess.
the water here has a line in it. This is actually from that model. But I'm afraid I can't answer the question in detail.
Like if you were to pull down the hydro data from the planimetrics, you'd see how it's broken out, and it's probably quite simply.
Because, the water bodies are not lots.
Right.
Fair enough. Yeah.
I also think that some of the parks are really segmented polygons.
The parks, the number of parks here, 16,000 parks.
I think it's partially because.
That would make sense. Yeah. Yeah, 'cause, where's the one number that says it's 1 million buildings, but it's 4 million objects? Yeah, here it is, 4 million objects, 1 million buildings. I lose count after a while. So there was a lot learned with respect to building this model. And in fact, right now, Professor Kolb is, he's been involved in the underground project, so he's looking at the street level, like curbs and the sewers and the whatever, to be able to get ready for an underground model. So he's done that. He's also begun to integrate a dynamic data model about traffic. Dynamic data model, I think it was about traffic, he told me. You know, so you'll be able to see cars moving around in this city GML thing. So I don't know exactly what he's doing, but I can put you in contact if you have interest. So that's some stuff going on in New York City. There's a bunch of software that supports it. Well, so I give you a sense of the maturity of City GML as that it's been deployed like this. Where we're at now really is about validating the quality of the data. You know, you can exchange it, but how good is it? That's a different question. And so we have done some experiments and some work about defining quality validation domains of different types and getting rules that go along with that. So you've got a set of machine language-oriented rules, and then a set of services that can take those rules and apply them to a City GML data set and produce results that say, here's the problems you have with geometry, here's the problems you have with attributes, that kind of thing. So it's about taking the structure of a City GML model, given that it's very mature, and the ability now is to check the data inside of it. That's the level of maturity in technology advancement. You know, it's a little bit different. You're familiar on the left here with some invalid polygons in 2D. You get some more interesting things as well. Things get more complicated in 3D. And so how to check quality of valid solids becomes a question and the like. So advances in that area, and rule checkers. That's kind of one area of advancement now, as people are putting out engines to check the quality of City GML data automatically based on a set of rules. That's kind of where we're at. Okay, so that's kind of an overview of some of the tools that are available, in particular about 3D modeling for urban environments. What I'll tell you now is about two projects, one that's done and one that's underway. The underground one is started. One that's complete, though, is this future city pilot, and phase one is complete. As of December 2016, and they've been packaging up the results for 4 months. And there's 3 scenarios I'll lead you through: urban planning, urban flooding, health alerts, and dynamic modeling. These are based in European cities, sponsored by a set of European organizations, but the results are globally applicable. Let me give you a sense of what was done there. Urban planning, so in the same way of quality, you can do rule checking based on urban planning. And so if you've got a set of rules for what your buildings, as they're being put in for approval, need to satisfy, you can do automatic checking of the plans that come from the AEC firm as it's brought into your integrated 3D urban model. So it matches up with the BIM community, the Building Information Models. IFCs are the standards that the BIM folks use. This is all the architecture, engineering, and construction firms. There's becoming more and more requirements that when people build buildings, they deliver electronic BIM files for those buildings. Those BIM files are then used in a City GML fashion, because you don't need all of the detail of a BIM model. You don't need the construction detail. You need the urban scale model of what a building is about to do some of these rule checks about heights and angles and a variety of other rules that were implemented. And so there was an automatic system to do that. In fact, it looks something like that. It uses a WPS on a set of databases, set of urban planning rules, and set of results that come out and say, okay, here's the things that don't match the urban planning rules, go back and change your plan. That's number one. Number two, in future city planning, was about coastal inundation. So this, they make a contrast between the traditional transformation of some flood data into a GIS layer and then display of innovation. The advancements then is to make that much more dynamic and much more higher resolution with respect to the floodplain in 3D. And so a set of models from some rather robust flood model predictions that are then created into a 3D city GML encoding and placed into a GIS environment with a much higher, much richer inundation, richer prediction of inundation in flooded areas. So we did that. We also did that with San Francisco with a storm that came into the bay with a city GML model and an inundation model that was much richer. So that's the second one. The third and fourth one are about dynamic processes. This is about adding dynamic variables to what has traditionally been static information in your GIS databases. So this is about taking an encoding city GML and overriding the static objects with time variant values from sensor simulations, external files. So you have the urban 3D model already existing in a static format, but you want to be able to use real-time data to see how that it looks like in that model. You want to do visualizations on it, you want to do analytics on it, but they need to be at the right geometries, in the right place, and the right features in the city GML model. So scary stuff ahead here. This is some object diagrams. This is what actually is in the standards. And so there is an abstract feature type that's already defined for city objects, and this is adding what's called a dynamizer. I love this, dynamizer, right? I mean, a bunch of engineers got together to come up with a term for, it's the dynamizer. So, and it's about adding time series, and you need to have different ways of doing time series. And bringing those observations in. You can have repetitious patterns of time series, you can have composites, different calendars, different schedules, and that kind of stuff. And then to be able to bring in the observations, the actual measurements of the data, and attach them to the city object. So, that's more than you probably bargained for when you came here today at lunch, but there you got your object model of the week, right? So they applied this, so now we can attach dynamic data to the software that was the urban 3D models. That's a big deal. That's really advanced. So how would we make use of that? One way, this third scenario was about health alerts. So looking at an urban environment, looking at temperature and humidity, and what buildings are the worst and what rooms are the worst with respect to that, especially with respect to senior living facility was the one that was looked at, and the temperature and humidity over time, and who should be evacuated. Should we take action to get somebody out based upon this prediction? And so that was the scenario there. The fourth scenario was about solar energy production based on roofs and facades. You're probably aware of the level of advancement of Germany with respect to solar energy. It's just amazing. They are the leader, I think, in the world about solar energy. We might try for that someday.
4 years.
Pardon me?
In 4 years.
In 4 years. Yeah, there you go. So, in any case, they added the dynamizer to City GML with a solar insulation, solar radiation per month to be able to determine the best location for solar panels, and then approach those folks with offers to make that done. So, that's the kind of stuff that was done in the Future City pilot, adding dynamics, looking at flood inundation, looking at urban planning. So that's what an urban model can enable a city to do, is those kinds of advanced understandings of their 3D environment, semantic environment, and the like. We're going to do some more, maybe looking at indoor facility management. There is some interest in VR and AR in that as well. Not sure where that's going to go yet, but very interested to chat with you about that, Neil, and see where it goes. All right, so let's finish off then with the project that's most exciting, because it still resonates in this room from 2 months ago, about underground mapping and modeling. So this is one of the frontiers, if you will, of 3D urban modeling, is underground, and in particular underground infrastructure, 3D semantic modeling of utility networks, and the underground environment, because it's all filled in with soil and it sits on bedrock, and so we need that underground geologic, geotechnical environment, as well as the built environment that's underground. There's some really strong ROI benefits. Here's one, I'll show some others. It's underway right now as a study funded by the Fund for the City of New York, thank you, Al, by the Singapore Land Authority, and the Ordnance Survey of Great Britain. We had a workshop here, and we aimed in April, and we're working up to publishing the report and getting a pilot underway before the end of the year. So let me give you a sense of what this concept development study is an activity that we do in OGC when we know we want to do some kind of a pilot implementation and the like, but we're not quite ready to say go build code. We might want to think about it a little bit more and kind of get the framework, the architecture, the agreement about terminology, the data models in place before we get a collective action of a pilot. That's what a study does. It does it in a concept development study. We released a request for information, so there's a public release of that. We got 31
26.
Responses.
It's more than that.
We had a workshop here 2 months ago. We're developing a report right now. Here's the responses to the underground RFI, request for information. And it was a good mix of, again, governments, universities, and commercial companies. It was also a good mix of the US, North America, Europe, and Asia. So really felt, pleased about the response that we got with respect to that. We held a workshop focused on looking at what cities are doing something now. What are their information system practices they're doing? What are the data models that come out of that? What about the underground, the geologic stuff, and then kind of their systems activities, and then a recommendation. So this is kind of the conceptual slide of what we're aiming to do. The aim is to address a set of use cases based upon the available data sets that are in various locations. So you got a distributed data set environment. Each agency holds that data as its goal, as it should, because it spent a lot of time curating and building that data set, and so wants to make sure that it's used accurately and not released where it could do damage. So a whole lot of organizational issues about getting to some kind of a secure and safe interoperable environment for all of this data that goes after these underground use cases. So what you'll see now is a set of slides that came from the individual presentations, which gives an indication of where we're at. Everybody's kind of giving their ideas right now. We kind of got a general picture, and we're merging down to some collective distilled wisdom knowledge, hopefully, about this area of underground environment. This is the way Singapore sees that same problem and the challenges associated with it. This is what the Ordnance Survey sees as the challenges and the problems associated with that, and including the one that's really easy to see on return on investment is the one that comes out of Chicago. Accenture is the leading organization in that group that's doing a pilot in Chicago. But this is data from Pennsylvania DOT at 21 times the return on investment. If you accurately model the underground environment, that's the kind of payoffs that you can anticipate. So as we plan for a pilot, this is good rationale for why we should be doing this. See that? So some use cases. One of the primary use cases is this, where do you dig and how do you dig? The subsurface utility engineering use case. We got some wonderful pictures of excavations and all kinds of stuff going on. Then if you've got the models and the ability to pull the data together, especially when you're looking at cascading effects, you can begin to do modeling of what's going on underground. This is a use case that came out of Munich, explosion in a distribution station affecting the power grid and people and the response to that. This is, there were several organizations that put up slides about augmented reality because you can really virtually open up do the excavation and see where things are at if you've got good registration and accurate data. So as far as the proof of concept, people are doing this now. The question is really the quality and the accuracy of the data and the integration of that data. So looking forward to that. So what we aim to do is bring together a set of data sets from a variety of locations and be able to give some kind of meet these use cases based on that data. The challenge, of course, is those data models and the schemas are all very different. So you get different data models, you get different representations of geometry. This goes back to how does GIS do geometry versus how does CAD do geometry. They are different, and so how do you address that? Not only are they different in terms of their basic geometry, they're different in terms of the semantic attributes, and they may call the same thing by something different, or they have different terms. So those are the challenges. This was an interesting presentation by Discrete that listed all of the different standards for all the different data models that they currently already support with respect to bringing this data together, and they're saying, make this problem easier. How can you reduce the complexity of this problem? So what we're aiming to do, and what's already underway, is an extension to City GML for underground utility networks. And so be able to have the right, have a geometric description as well as a semantic description of the underground utility networks. That's where we're at. It'll match up with what's an OGC called land and infrastructure modeling, and the encoding known as infra-GML for these wastewater, storm damage, underground utilities, water distribution layers. There's also some really key data standards coming from the American Society of Civil Engineers, which this is the quality levels, the A, B, C, D level. So the least accurate is that you've had some verbal record. Somebody told you it was underground. Well, that's helpful. Versus you've actually exposed and verified that it's put some kind of a survey instrument on the underground feature, and so it's a quality issue because it's hard to see where things are at underground. The other thing that ASCE is moving towards is the as-built recording and exchanging of utility infrastructure data, and this is moving towards becoming standard practice for civil engineers with a level of accuracy required for different activities, and that's called out in that standard. So we've got all these utilities. There happens to be soil in between the various utilities, tunnels, and foundations, so that soil is really key. We had Columbia University, George Diodatis, give us a really good perspective. He's got this collection of boreholes under the city, under Manhattan. It's really a tremendous wealth, and if you know him and you wink right, you might get some, but they are a rather controlled data set because of they're proprietary with respect to construction organizations. So, but what it tells you is, there's different soils underneath. They move around differently based upon the types of soil and the bedrock that's underneath that. A couple things that underground environment drives in is maybe some different ways to model. So we had a study by a couple folks from Delft that were here over last summer. It's almost a year ago now. But they brought us some perspective on maybe using voxels as a way to model the underground environment with multi-resolution object databases to do that. So some interesting advancements. It's early for that in the sense of standards, but really good research. Leads to the ability to do modeling. Once you've got that full model of the structure and the surface and the like, you want to do dynamic modeling. This was underground water cycles affecting the underground and the architecture that goes along with those data models and the like. Let me finish off by giving you a couple examples of systems that are operating right now. One is actually required by law. It's this CLIP system in Flanders, underground utility location system, and how they serve as a central integrator or distributor, depends on how you look at it, with respect to getting requests for what's underground here before I dig, that kind of stuff. And it's 3D and required by law. That one's only 2D, isn't it?
I think so.
What they deliver is a map.
Mhm.
Yeah,
It may be
the
3D.
inputs.
I'm not sure.
We're still learning. The other one is Chicago has this version of a variety of data inputs, having some kind of a database based on GIS. It's a GIS database. We're not quite sure what the attribute structure they have there, how much is held in the inputs versus just the metadata. But then they tend to answer a set of questions using this 3D GIS, and they do describe theirs as a 3D GIS in Chicago, and it's very much a prototype right now, and we're looking to work more with them. So that's where we're at with respect to the study, trying to understand where we're at and where we're going. What we're going to be able to do is write the report, get a baseline, get a good understanding in the community, and then move towards implementation, get some running code, get some interoperable interfaces, get some demonstration of why it matters, run some scenarios like urban planning and opening the ground and the cascading errors, those kinds of things, all while addressing the heterogeneity of the data sets that are coming in, the need for some kind of a central model, data model for the underground environment, and recognizing the secured online access because of the data that we're dealing with. So that's it. That's the last of the discussion. That's our underground. Let me leave you with, what we focus a lot on is the innovation. Our organization really and the members really see benefit because they come and participate in activities that is relating to their research and development and their innovation activities. What that results in for the community is a set of standards that build out what is possible in the world, in the world of geospatial information and sharing of that data. So the benefits of an open standard approach. And now we're looking not only at an above ground urban model, but all of that underground urban model. This is London. This is from the Ordnance surveys. Where's the shard? Here's the pickle, right? That's the pickle, and what's called the shard. And, okay, so hopefully that was interesting to you about 3D urban modeling, some advances with respect to how it's applied in smart cities, the future city pilot, various use cases that I gave for you, and then give you a sense of what we're doing here in the city about underground and where that's going. So if any of that sounds interesting, come and get involved, but certainly if you have any questions, I'd be happy to entertain.